Okay, this is a solution video for abstract inequalities. It's exercise 12.5 on page 464 and it's question 11. So the question starts off with a few terms and conditions that p is greater than 0, q is greater than 0 and p is not equal to q. And on this basis we're asked to prove that p plus q over 2 is greater than the root of pq. So the obvious thing to do here is to square both sides and to work away with the inequality and try and get everything on the left hand side. To do that, I'm going to first of all start off by making the assumption that this statement that I want to prove is true. And I do that by making an if-then statement. So I'm going to say, well, if p plus q over 2 is greater than the square root of pq, then the left-hand side squared is greater than the right-hand side squared. Now, this is the reason, by the way, that they gave us this information at the start to begin with, because if p is positive and q is positive, then it means that p plus q over 2 is positive, and the root of pq is positive. And if the left side is here greater than the right side, then when I square, the left side will remain greater than the right-hand side by virtue of the fact that they're both positive values initially. And now I'll just go ahead and do a little bit of tidying up with this. Just remember that when I'm squaring out a bracket like this, the power is distributive over division, which means that I must square the top and I must square the bottom. And just be careful that you square the top properly. So I end up with p squared plus 2pq plus q squared over 4 is greater than pq. And then I'll bring the 4 across and multiply. And then I'm not particularly liking this 4pq over here on the right-hand side. Generally, when we're trying to prove inequalities like this, we're trying to prove that something squared is greater than 0. So I'm going to bring everything to the left-hand side and see if I can manage that. And of course, once I do that, then I can see that I've got two like terms here on the left-hand side, 2pq and minus 4pq, which I can put together to get p squared minus 2pq plus q squared is greater than 0. Now, I don't know for definite if this is true just yet. I'm just working on the basis that this is true if this statement up here was true. So I don't know if it's true, but if I can prove that it's true, then I can work my way back up the chain and state that the initial statement was true. So I'm going to have a look at this and notice that, okay, well, p squared minus 2pq plus q squared is actually a perfect square. So I can say that p squared minus 2pq plus q squared is actually equal to p minus q squared. And I know something about this, and this is really the key to the whole proof. P minus q squared is definitely positive. It's definitely greater than 0 because it's a square. And in previous questions, we've said greater than or equal to 0 because sometimes squares can be 0 if the original value is 0, obviously. But in this question at the beginning, they actually made the point of stating that p and q were both bigger than 0. So they're both positive numbers. So p minus q squared then must also be greater than 0. And since I'm making a statement here, I want to back it up if I can with a reason. So I'm going to say that a square is bigger than 0 in this case. So this implies, and I'm working my way back up the chain now. So first of all, I'm going back here and saying, oh, I should really have brought my arrow slightly further back. So that brings me back as far as this line here. So if this is the case, well then this line must be true. And then I'm just working my way back up through the other landmark statements of the question. So I can link that back up then to this statement here, because really this line came from this line originally. And then I can link that back to my initial supposition, which is what I was actually trying to prove. And since this is my final statement, I'll say, therefore, p plus q over 2 is greater than pq. And you can stick a QED in there if you like.